Time. As Mr. Webster defines it, a measurable interval, or a period between two events in which something happens. Time. Aviation runs to its beat. In fact, its success is often rated in terms of being on time.
Bob, what was our off time?
Sometimes, however, being on time is not either possible or prudent. And more often than not, you'll find that at least one of the reasons is weather.
Folks, this is the captain speaking. We're observing some bad weather on our radar ahead of us. And to avoid that, we're going to delay our approach for approximately 20 minutes. So please keep your seatbelts fastened, and we'll get back to you with an update as soon as possible. Thank you.
How do time and weather fit together? Well, one particularly dangerous weather phenomenon that must be avoided is severe wind shear. And in the next few minutes, we want to demonstrate how a flight crew can improve its ability to avoid this hazardous condition. And about that critical time, maybe no more than 5 seconds, in which flight crews must react quickly and correctly if they do encounter an unexpected wind shear on takeoff or landing. But let's start by understanding that the only safe wind shear is a wind shear avoided. Severe wind shear, as far as aviation is concerned, is most often defined as a rapid change in wind velocity and/or direction that results in an airspeed change of more than 15 knots, or a vertical speed change of 500 feet per minute. A severe wind shear encounter on takeoff or on approach should be considered very serious, since a pilot has less altitude and time in which to recover, as well as takeoff and landing being the times at which the flight deck workload is heaviest. The statistics speak dramatically as to how lethal they can be. In the decade from 1976 to 1986, wind shear-related accidents accounted for nearly 40% of the fatalities resulting from accidents in major air carrier operations in the United States. With air traffic in the U.S. on the increase, the exposure to significant wind shear conditions will also increase as more flights arrive and depart at times and places where the potential for a wind shear encounter exists. Wind shear can result from a variety of conditions. However, the most severe and dangerous shears are produced by either non-convective frontal conditions or convective air masses such as thunderstorms. Thunderstorms develop as a result of either localized heating at the Earth's surface or warm, moist air moving up and over cool air in both warm and cold fronts, causing convection. As the moist air rises and is cooled, precipitation develops, creating a vertical downflow, which spreads out horizontally in all directions. In a typical thunderstorm, the downdraft area is fairly large, from 1 to 5 miles in diameter. And although the outflow may produce a large change in wind speed, it occurs over enough distance to reduce the effect on aircraft. However, the smaller in diameter and potentially more dangerous convective wind shears, known as microbursts, are a serious threat to aircraft. The downdrafts associated with a microburst are generally only a few hundred feet to a half mile in diameter. This rare time-lapse film shows the life cycle of an actual microburst. The time span is compressed from almost 7 minutes to 30 seconds. At the onset, the heavy rain core from a thunderstorm can be seen. And as the microburst develops, the downflow diverges into an intense outflow near the ground. In addition to sustained downdrafts, short-duration reversals in vertical winds can exist due to the horizontal vortices associated with microbursts. To the left of the microburst, a cloud formed by an updraft associated with the vortex is also visible. Microbursts may not be symmetrical, and the outflow on one side of a microburst might be less severe than the outflow from the other side. Wet or thunderstorm microbursts are most often associated with heavy rain, whereas dry microbursts occur in situations where there is virga, which is precipitation that evaporates before it reaches the ground. The virga associated with microbursts originates from high-based convective clouds. Research indicates that the average wind speed change in a typical microburst at its peak intensity is nearly 50 knots. The typical microburst will intensify for about 5 minutes after it first touches the ground, and during that time may increase up to 3 times its original strength before it starts to dissipate. It's very important to understand that some microbursts cannot be successfully traversed using any known piloting technique, so it is critical to avoid all known severe wind shears. Unfortunately, there is no definitive detection and warning system capable of measuring the existence or intensity of wind shear along the intended flight path. However, there are some very important clues that indicate the potential exists for microburst wind shear. For instance, we know where a microburst encounter is most likely. This shows, from high to low, the frequency pattern of U.S. thunderstorm activity. And since some microbursts are associated with these storms, the areas with the highest probability of a thunderstorm-related microburst can be identified. We also know that the relatively arid conditions in the intermountain and high plains regions of the United States increase the potential for dry microbursts in those areas. Pilots should also evaluate the weather at their departure and destination airports for any indication of wind shear. Weather reports calling for gusty winds, heavy rain, or thunderstorms should alert pilots to the potential for wet microburst conditions. And a report of a 30 to 50 degrees Fahrenheit temperature dew point spread should be a warning that conditions are right for microbursts. In some cases, terminal weather forecasts may also include a low-level, meaning low-altitude, wind shear forecast, derived from National Weather Service observations. A pre-flight weather evaluation should also include a check of convective sigmets. These reports concentrate on weather conditions that are particularly hazardous to aviation. An equally important part of the weather evaluation routine must be done by flight crews prior to departure or approach, since there are also visual clues as to the presence of wind shear. For example, thunderstorms, virga from high-based clouds, localized blowing dust, especially in a circular or elliptical pattern, rain shafts with rain diverging away from the core in all directions, or any indication of tornado-like activity, such as funnel-shaped clouds or actual tornadoes. Since, with the exception of lightning, these clues are not visible at night, special care should be taken during non-daylight operations because microbursts can occur wherever there are convective storms. In addition to visual clues, other sources of information about potential wind shear activity are also available. One of these, the Low-Level Wind Shear Alert System, called LWAS, is in use at over 100 U.S. airports. The system is designed to detect wind speed and direction variances between 5 or more outlying sensors and a reference sensor located at or near center field. Since some microbursts are so small in diameter they can pass between sensor stations, the system is not as effective in detecting this type of wind shear. However, if preset limits are exceeded, air traffic control will report the relevant wind information to aircraft in the terminal area, which should be considered by pilots as an indication of the presence of wind shear. Pilots are also urged to use their onboard radars to scan for convective weather echoes in the immediate terminal area as a potential indicator of wind shear. Although in some cases, such as the dry environment microburst, a hazardous wind shear may reflect weak echoes or no echoes at all. And as you can see here, even if the radar is monochromatic, its use is equally effective in identifying convective storm cells that could indicate potential microburst activity.
Wind shear pilot reported on 1 mile final by DC 10, airspeed loss of 15 knots.
One final point about wind shear avoidance. One of the best sources of information is pilot reports, or PIREPs as they're called. A wind shear PIREP should cover the location where the shear was encountered, an estimate of its magnitude, and the type of airplane involved. Pilots are also encouraged to include a plain language description of what occurred, since this can often be a more clear warning than anything else of exactly what to expect. A wind shear PIREP should alert other approach and departure traffic, since it is known that microbursts can intensify very quickly. These clues should be kept in perspective, since some are obviously of greater importance than others. And in most cases, the greater the distance any of these clues occur from the departure or destination airport, the less relative importance they have. However, it is also important to understand that each piece of wind shear evidence is cumulative, and if more than one of these indicators is present, the potential for microburst wind shear activity is higher. Pilots, however, can and do inadvertently find themselves in significant wind shear situations, and it is important to understand exactly what effect severe wind shear has on an airplane. In this instance, the wind shear is symmetrical, so the headwind at the onset of the encounter would act to increase airspeed. However, in the downdraft and tailwind producing outflow areas of the wind shear, the decreasing airspeed may produce a high rate of descent. Wind shear has been recognized as being a threat to aviation to the extent that a major industry-wide study was undertaken in 1986 to analyze past wind shear accidents and incidents. A team of pilots, engineers, and meteorologists investigated all elements that could have conceivably contributed to the accidents. The first step in the process was to review accident and incident data, so models of the wind components could be recreated. These wind models were then used in piloted simulations of routine takeoffs and landings in which ordinary flight techniques were employed. In almost every case, the pilot's reactions were nearly identical to information recovered from the flight data recorders. This accident and weather data was then used to reconstruct each event to determine what occurred. Was sufficient airplane performance available to have prevented the accident? And if so, why was the potential performance capability not used? The two most important conclusions were that the onset of a wind shear encounter was often quite difficult to recognize, and that there was very limited time available, often no more than 5 seconds, to react appropriately. The analysis of after liftoff wind shear encounters showed that although initial trends in airspeed, pitch attitude, vertical speed, and altitude may have appeared normal, if the wind shear was encountered before a stabilized climb was established, it was more difficult to detect. And without immediate recognition, as the airspeed decreased, the loss of lift and natural pitch down tendency of the airplane to regain trim airspeed resulted in a reduced climb rate and a loss of altitude. In some cases, pitch attitude was allowed to decrease 5 to 10 degrees below the normal value before the crew took corrective action to control the flight path. In many cases, this required using unusual stick forces. However, if pilots took this action and accepted the low airspeed, critical flight path degradation in most cases could be prevented. It was also found that training emphasizing a reduction in pitch attitude as the response to the decreasing airspeed delayed the appropriate action. In their analysis of wind shears encountered on the runway, they observed that timely recognition was also a problem, since the only indication might be a slower than normal airspeed increase, which could be difficult to recognize as wind shear if there were gusty winds. If a reduced thrust takeoff was used, an immediate increase in thrust was necessary to provide increased performance potential. It was also noted that if insufficient runway remained to accelerate to the normal takeoff speed or stop safely, pilots should initiate rotation at less than the normal rotation speed. However, liftoff under these conditions required the use of higher than normal pitch attitudes and control forces. Survival in an on-the-runway encounter could depend on a pilot's ability to overcome previous training and use a higher than normal pitch attitude. On approach, the researchers noted that in some cases, a decreasing performance trend could be masked by gradual increases in thrust. They also speculated that poor weather conditions often associated with wind shear caused an increased workload and detracted from proper instrument monitoring, which contributed to a delay in recognition of a wind shear encounter. The last phase of the research focused on determining if there was a recovery technique or procedure that would aid pilots in the event of an inadvertent wind shear encounter. Many different techniques were evaluated and tested, taking into consideration microburst characteristics, airplane performance, and the need from a human standpoint to keep the technique as practical as possible. The result was a technique which, although not best in every situation, was most effective in a wide variety of situations. Simply stated, the recovery technique involved the use of pitch attitude and thrust to restore or maintain flight path control. The final conclusion of the study was that flight crews needed a plan or process to assist them in dealing with the possibility of wind shear. The result is a simple series of flight crew actions that can be applied on every flight. The first step is to evaluate the weather and ask the question, are there any signs of wind shear? This action recognizes that avoidance must be regarded as the absolute first line of defense against severe wind shear. The second phase of the process is to ask the question, is it safe to continue? A takeoff or approach must be delayed until the answer is yes. The next action is to consider the use of precautionary procedures when no serious threat of wind shear actually exists, but some of the indicators are present. They include using maximum rated thrust levels, considering the use of recommended flap settings, using the longest suitable runway, considering the use of increased takeoff rotation and approach speeds, and whether or not to use automated systems. The next step, the use of standard operating techniques, should be practiced on every takeoff and landing, since they increase crew awareness and coordination. Crew awareness involves developing a knowledge of normal flight instrument values of pitch attitude, rate of climb or descent, and airspeed, so deviations from normal values that might indicate the early onset of a wind shear can be recognized. Crew coordination involves understanding crew roles and the use of clear, standardized call-outs by the non-flying pilot to indicate flight path deviations.
Losing airspeed. Max power. 40 feet. Climbing.
In this way, the entire crew is involved in the all-important task of looking for cockpit indications of wind shear. Should an inadvertent wind shear encounter occur, immediately on recognition, the crew must perform the final phase of the flight crew actions, the recovery. The key points in the recovery procedure are: thrust must be applied immediately and aggressively, avoiding engine overboost unless necessary to ensure airplane safety. Pitch attitude should initially be adjusted toward an attitude of approximately 15 degrees. If the resulting flight path at 15 degrees is not acceptable, a pitch attitude in excess of 15 degrees may be required. However, to avoid stick shaker and maintain adequate margin over stall, the pitch attitude may need to be reduced below 15 degrees. Airplane configuration. Flaps and landing gear should be maintained until an acceptable flight path is restored. One final point. Make a pilot report of the encounter to air traffic control as soon as possible. This is important since microbursts are known to intensify rapidly, and a following flight may encounter a non-survivable shear. Remember, the only safe wind shear is a wind shear avoided.